Hey everyone, welcome back to the channel. In today's video, we are going to explore Principal Component Analysis or PCA. It's a powerful technique for dimension reduction. And you have probably heard about it, but how does PCA work in practice? And how can you use it to reduce the dimension of a dataset while still retaining the important information? We will be working with the Wine dataset, a classic dataset in machine learning that contains 13 features describing different chemical composition of wines. And by applying PCA, we'll reduce the data to just two dimensions and visualize the results. Here's what we'll cover. So understanding of the PCA and its purpose, implementing PCA in Python with defined dataset, visualizing the result before and after applying PCA. So let's dive right in. So what is principal component analysis, PCA? It's a technique used for dimension reduction. In simple terms, when you have a dataset with large number of features, PCA helps you compress the data into fewer dimensions while preserving as much information as possible. The principal component are new axes in the feature space that capture the most variance in the data. PCA transforms the original data into a set of linear uncorrelated variables ranked by how much variance each capture. It's especially useful when you're dealing with a data set that have many features and you want to visualize or simplify the data while keeping its structure intact. All right, now let's jump. This is the principal component analysis depiction where, as you can see, there are three variables in the original data, and we are trying to reduce into the lower dimension data set with two components. So we will be doing the same thing with the wine data set. All right, let's jump into the code. We'll be using the Python for this, and the libraries we need are NumPy, Pandas, Matplotlib, and C1 for plotting, and scikit-learn for loading the wine dataset, scaling the data, and applying PCA. So I will just import this libraries, and now let's load the wine data. This data has 13 features describing the chemical composition of different wines, and it's already built into scikit-learn. We'll load it and take a look at the first few rows of the data. As you can see, we have 13 features in the data, and the target variable y represent the wine class. So this is a classification problem with three classes. Next, we need to standardize the data before applying the PCA. And before we do this transition, I would like to highlight the fit transform and fit transform. So these are three functions available. So we use fit, so it just compute the mean and standard deviation to be used for later scaling. Now it's just a computation with no scaling done. So dot transformation uses the previously computed mean and standard deviation to scale the data. And fit transformation, which is this function, it does both at the same time. And you can do it with just line one code. That's why we are using the fit transformation here to standardize the data. And now that we have standardized data, let's apply the PCA. Will reduce the data to just two principal components so that we can easily visualize it. And we'll check how much variance each components capture. So let me apply the PCA here. And here the explained variance ratio, it tells us how much the total variance is explained by each principal component. And the sum of two value will give it how much information is captured by just the first two components. So this much is the variance. This is the total variance. And now let's visualize the PCA transform data. So if I run this, so this is the plot of 2D using the first two principal components and the color point based on the classes label so that we can see how well the PC has separated different file classes. As you can see, there are three classes, 0, 1, and 2, and that's how it's been differentiated using the PCA. And as you can see in the plot, the vine are well separated along with the first two principal components. Each class is clearly undistinguishable, showing that the PC has effectively captured the main structure of the just two in just two dimension. Right? Let me visualize the original data set. And let's compare the result. First, we'll look into the original high dimensional data. Since we have 13 features, we can't plot all of them in 2D space. We can visualize it using the pair plot. It will take some time to populate. Yeah. So the pair plot shows the pairwise relationship between all features. And as you can see, it's a bit harder to get the clear sense of a data since there are so many dimensions. And now let's go back to the PCA transform data, which this is the same, which was same graph, which we same scatter plot, which we just saw. As we have already visualized the PCA transform data, where we reduce the dimension to just two principal components. So you see, as you can see, the PCA plot is much easier to interpret compared to the pair plot, right? And it clearly shows how the data is separated along the two principal components. This dimensionality reduction makes it much simpler to analyze and visualize high dimension data. So to wrap up, PCA is a fantastic tool for reducing the dimensionality of your data while retaining the most important information. We saw how the PCA how to apply the PCA to the wine dataset, reducing the 13 dimension to just two. And we compare the original dimensional data with the PCA transform data. And clearly PCA have made the data much easier to visualize and analyze. I hope this video helped you understand the basic of PCA and how to apply it in. Thank you for watching. I will see you in the next one.